Hello and welcome again to another lesson on integration. This one's the fifth one of a series of, I'm planning about 12 or 13 in truth, for year 13 Edexcel integration. This is going to focus on using use substitutions which are either given to you to use, so you might either be told by an examiner to use a particular substitution, so you have no leeway, you can't just do your own thing, or sometimes an examiner will say something along the lines of use a suitable substitution to do blah blah blah. So sometimes you'll be forced into doing a substitution either because the examiner is wanting to test those skills or because you have to and there's no other way without going beyond the specification for A level. So I'll come on to that in a moment. Sometimes these substitutions are quite tricky, so I've built in a few more worked examples. But before we get on to that, let's of course do some warm-ups. So this time I reverted back to giving 4 of you to try. Question 1 and question 3 are proofs. Question 1, I want you to remember the proof of root 2 being irrational. So the clue for question 1, go back to your notes, think about the proof of root 2 being irrational, and then adapt that to the proof of root 5. This probably won't be examined, but it's a good practice one. And question 3 here, this is one of these things you need to know how to prove. The examiner could ask you this more or less in this exact same way I've put it here. Okay. So have a go at those, press pause now, then play when you're ready to see the solutions. So let's have a look. Prove that root 5 is irrational. Importantly, you need to be able to assume without proof, unless you want to waste your time, that if n squared is a multiple of 5, then n is also a multiple of 5. This, in brackets, you could prove yourself, and it is fairly straightforward to prove actually. It's in your skills for an A-level student. However, if a question is giving you a get out, then it'd be foolish not to use it. So let's have a look what the proof should look like in essence. So what we're going to do first is we're going to assume that root 5 is rational, and therefore we're going to set root 5 equal to a over b, because any rational number by definition can be written as a fraction where a and b are natural numbers. And also we need to say that a and b have no common factors. This is a very, very important thing to add on. We're assuming, therefore, that a and b is a fraction in its simplest form. That is absolutely key. So either say a and b have no common factors, or say the fraction a over b is in its simplest form, an absolute must. So if we were to square both sides, 5 would equal a squared over b squared. If I multiply both sides by b squared, you can see that a squared must therefore be 5 lots of b squared. So in other words, a squared is some multiple of 5. A squared is 5 lots of b squared. So since a squared is a multiple of 5, a itself is also a multiple of 5, using this handy information that was told to us in these brackets. Let a therefore be 5 times k, where k is just some natural number in itself. So essentially, instead of calling it b squared, I'm just saying b squared is going to be some natural number as well, because a natural number squared will be a natural number too. But by calling it k, it just simplifies the next step, and also k is an element of the natural numbers, reads like Ken, which will never fail to amuse me greatly. So square both sides, a squared would be 25k squared. If I now plug in a squared being 25k squared into this equation here, then we now get that 5 must be 25k squared all over b squared. That rearranges, so we can hopefully see that b squared is 5 lots of k squared. But if b squared is 5 lots of k squared, that means that b squared also is some multiple of 5. And using again in brackets what we had here, if b squared is a multiple of 5, we can say with confidence that b itself must also be a multiple of 5. But we said before that a was a multiple of 5 too. So a and b are thus both multiples of 5. So they've got a factor of 5 in common, but we said here they should have no common factors. So this contradicts our assumption that a and b is a fraction in its simplest form. We've followed through the logic step by step flawlessly, we've not made any slips with our thinking. The only conclusion therefore must be, if we followed it through logically from an initial assumption, and our logic was correct in each step, the only way we could come to a nonsense here, or a contradiction, is if our initial assumption were incorrect. Our initial assumption was that root 5 is irrational, that therefore must be incorrect, therefore our final conclusion is root 5 has to be irrational. question 2. Differentiate these with respect to x. So the first one, we've got 3 sine squared x, and this one here is sec 2x. So d by dx of 3 sine squared x plus sec 2x. I'm going to use the chain rule for the sine squared x. So I'm not going to go into depth with it, I'm just going to explain what I'd do. I'd set u to be sine x, so then sine squared x is u squared. But essentially you should see that if I differentiate this, I'll get 3 lots of the derivative of sine squared. Think of u squared, so that'll become 2 lots of sine x multiplied by the derivative of sine x itself, which would give cosine x. And this here, differentiating sec kx, where k here is 2, k is a constant 2, is a standard result given to us in the formula book. And so what will happen here is that 2 will come to the front because of differentiating, and sec differentiates to tan multiplied by sec. And so that gives us 2 lots of sec x, sec 2x, almost made a slip there, sec 2x, we've got 2x here, tan 2x. So expand out, we get 6 lots of sine x cosine x plus 2 lots of sec x, sorry, sec 2x, keep saying that, tan 2x. Now there's another way this could be written, which may be the one which seems most obvious to you. Another thing I could have said, a different form, which is completely equivalent, is if you spot here 2 sine x cosine x, that's equivalent to sine of 2x using the double angle formula. So what I could have said is we had 3 lots of sine 2x plus this. So either way around you want to write it, I could have put it's 3 lots of sine 2x plus 2 lots of sec 2x tan x. So it doesn't matter which form you use as long as it's a correct version. Differentiate this one now, x plus ln 2x plus 3. I'm going to just call this whole thing equal to u cubed. So call that y, and then y can be u cubed, where u is x plus ln 2x in the brackets. So, applying the chain rule, dy by dx gives dy by du multiplied by du by dx. So differentiate this with respect to u, that's going to give 3u squared, and then differentiating this in here with respect to x, x would differentiate down to just simply 1, and ln of kx, where k is any constant, just goes to 1 over x. So in simplifying, I've got 3 lots of u squared, so it's 3 lots x plus ln 2x all squared multiplied by 1 plus 1 over x. Question 3. Prove that there's infinitely many prime numbers. This is an absolute must-know. So step by step, there's a few different versions of the proof. The one I think is most elegant, I'm going to present to you here, ironically in my very inelegant, soft northern tones. So, assume that there are a finite number of primes and call the complete list of primes capital P. So, P is going to equal P1, P2, P3, P4, P5, all the way up to Pn, where n is the last prime number. Now let's introduce and define into existence another number, q. Let q be the product of all known primes, p1 times p2 times p3, all the way up to pn, then magically plus 1. This is the key genius move of Euclid. And therefore, the number q sounds absolutely obvious, and it is. Q is either going to be prime, one case, or the second case, it's not going to be prime. So we just need to consider the 2 separate cases to arrive at our proof. So first off, if Q is prime, it's obviously, I hope to see, it's going to be larger. It's going to be a much larger prime than any of the individual P1, P2, P3, Pn's, because it's a massive product. And even if you don't think the primes are infinite, hopefully be convinced in thinking there's an awful lot of them, thousands. So the product of all these is going to be huge. So therefore, Q, if it were to be prime, is going to be an absolutely enormous one, bigger than any of the individual P's. Therefore, list P is going to be incomplete, because if Q is prime, Q is going to be a bigger one than any we've already listed in P. The other case is if Q is not prime. Well, if Q is not prime, then it must have some prime factors not already listed in P, because if Q did have some prime factors in P, if you divided them by Q, any prime in P would always leave a remainder of 1. So imagine dividing Q, for example, by one of the primes in here, let's say divided by P1. That divided by P1 would obviously leave a remainder of 1, as would any other prime in the list P happen to divide it by. So therefore, if Q is not prime, then it's got to have some other prime factor dividing it other than the prime in this list. So therefore, once again, list P must be incomplete via that reasoning too. So either way you slice it, whether Q being prime or Q not prime, the list of P has to always be incomplete. That is to say, you can never have a complete list of primes. So because a complete list of primes can never exist, that must mean our original assumption was wrong. The original assumption was to assume that they are a finite number. If that's incorrect, the conclusion therefore has to be that there are an infinite number of primes. There are infinitely many prime numbers. Question 4, we've got y, which is an algebraic quotient where x cannot be equal to 1 to save the universe from exploding when you try to divide by 0. Show that dy by dx is minus 8 all over x minus 1 cubed. So this one is going to be the product rule. Okay, so dy by dx of u over v is v u prime minus u v prime all over v squared. So that's where v is going to be x plus 1 squared and u is going to be the top function 5x squared minus 10x plus 9. So let's just apply the quotient rule and see what happens. So the first bit, I've got v, which is going to be, I'll get a long fraction in here just to get ready. So v is x minus 1 squared. I'm going to multiply that by the derivative of the top function u. 5x squared minus 10x plus 9 would differentiate to just 10x minus 10. The plus 9 will disappear entirely. I'm going to subtract away the top function u, which is 5x squared minus 10x plus 9, multiplied by the derivative of x minus 1 squared. You can either expand it out if you want to, I'm not recommending that, or use the chain rule, or just see. This here would differentiate to 2 lots of x minus 1. And all of that is going to be over v squared. So x minus 1 squared squared is going to be x minus 1 to the power 4. So what you can see here is we've got x minus 1 squared as a common factor in both bits of the numerator and also the denominator. So if I divide through both bits by one lot of x minus 1, I'll put it here to be explicit in terms of what we're doing, then this will cancel to power 3, this will cancel to just one lot, and that will cancel all together. So the next step, after doing that, we'll just have one lot of x minus 1 here, times 10x minus 10, and then we can have minus, the 2's not cancelled, so still minus 2 lots of 5x squared minus 10x plus 9. And all of that's going to be over x minus 1 cubed. Now, we want to show it's all over x minus 1 cubed, so we're on the right lines. We just need to simplify this top and hope it comes out to be negative 8. So, carry it on. Let's see what we get. So, the first bit here, the x minus 1 expanded out by 10x minus 10. We're going to get x squared, x times minus 10, minus 10x, minus another 10x, so minus 20x. Minus 1 times minus 10 gives plus 10. And so we get this. And then finally this part here, for minusing two lots, minus 2 times 5x squared. Oops, that said say 10x squared. I do apologise. That was rather silly. 10x squared there, sorry. Minus 2 times 5x squared, so minus 10x squared. Minus 2 times minus 10x is plus 20x. And then minus 2 times positive 9 is going to be minus 18. And all of that still over x minus 1 cubed. So next, we just need to simplify. So we've got here 10x squared, that'll cancel with a minus 10x squared. This minus 20x will cancel with a plus 20x, so we're going to end up on the top with just 10 minus 18, which gives minus 8. And so that's exactly what we wanted. So we've got minus 8 all over x minus 1 cubed. Hope you found those warm-up questions useful to get yourself in the mood. So assuming you are, let's have a look at some slightly trickier U substitutions. So part 2 of integration by substitution. So just a quick recap of what we've seen so far. So we've already seen how using U subs can be useful in simplifying integrals that would otherwise be difficult or even impossible to integrate. So although we now know when to apply a U substitution, at times a substitution might be required to solve an integral that is not obvious or intuitive. So in these instances, a question may be given where the substitution to use is explicitly stated, and unlike other U substitutions we've seen in the past, some of these substitutions will create expressions that do not cancel cleanly. So in these cases, what we need to do is we need to rewrite the original variable, usually x, in terms of a substituted variable, which is usually, of course, u. So let's have a look at sum together. So worked example 1, find the integral of x root 2x plus 5 dx by using the substitutions, first of all u being 2x plus 5, and then b being u squared equals 2x plus 5. So let's think about how to do this, and we can see as well that these two substitutions are both valid. So u equals 2x plus 5. So first off, take du by dx. So du by dx for part A will of course just be 2, and so therefore rearranging to get dx in terms of du, dx will just be du divided by 2. And so this integral here we can transform. So for part A, using this particular substitution, what we're going to get is x root 2x plus 5. Oops. That's just going to be u. So for this one, we're going to get x times the square root of u, which just means u to the power of 1/2. And then we've got dx, which we're going to replace with du over 2. But as you can see here, this isn't particularly helpful because I've still got an x, so I've got a mixture of different variables now. So this seems like panic stations perhaps, but as long as we keep our heads, we're absolutely okay. So like I mentioned in the preamble, what we need to do often is to switch the original variable in terms of what it would be in terms of the substitution. So what we need to think of here is what would x be in terms of u? So if we do that, we can solve it and not worry so much. Not that you should ever be worried about a maths question. So we've said, of course, that u is 2x plus 5. Rearranging, we get that 2x is u minus 5. So therefore, x is just going to be u minus 5 all over 2. So always be thinking, if you get dx in terms of du, and the du looks like it's not going to help in the cancellation, for example, dividing by 2 here certainly isn't going to help with cancelling the x, that's your clue that maybe I need to rewrite x or whatever it is in terms of u. So knowing that, what we can do, we can prepare and anticipate the same required move needed for this one here, which is u squared. So just get ready for the next one. I'll put this here when we move on to the second part, part B. But anyhow, now we know that x is u minus 5 over 2, we can change this integral so it actually will work absolutely fine. So we've substituted in for u, and now we can get rid of this x. So just doing it step by step first until you can see what's happening, and when you see what's happening and get used to it, then the fluency can come. So x is x, whoops, silly me, x is u minus 5 over 2, u to the 1/2 times du over 2. So dx been replaced, 2x plus 5 subbed for u, and then x in terms of u is u minus 5 over 2. We can now set to work. So dividing by a half and dividing by a half here, so I'm going to have a factor of a quarter coming out, which I'll take out now. So I'm going to have a quarter u minus 5 multiplied by u to the 1/2 with respect to u. So now if we just expand this, that's going to give a quarter. U times u to the 1/2 will be u to the 3/2, then minus 5 u to the 1/2 with respect to u. So that's going to give a quarter. So u, if I integrate this with respect to u, I'm going to increase the power by 1, which will become 5/2, then divide by that new power. Divided by 5/2 is the same as multiplying by 2/5, so that'll become 2/5 u to the 5 over 2 minus 1/2, new power becomes 3/2, then dividing by 3/2 is the same as multiplying by 2/3. So that's going to become 10/3 u to the 3/2 du. So then we can simplify this. So what we're going to get here is a quarter times 2/5. That would give 2/20, which goes down to just 1/10. So I get 1/10 u to the 5 over 2. A quarter times 10/3. That's going to give minus 10/12, which is minus 5/6. Again, running out of space seems to be often my mistake I often never learn from. Then, of course, plus c. So in simplifying and going back to the original variable, which of course was x, so always return in terms of the original variable, that's going to give us 1/10 u, which is 2x plus 5, to the power 5 over 2, minus 5/6, 2x plus 5, to the power 3 over 2, plus c. So that's our final answer here in this box. So, what if we were to use instead u squared equals 2x plus 5 for our substitution? How would that change things? Well, if u squared is 2x plus 5, I'm just going to rewrite the integral here for part B. So we're integrating, of course, x root 2x plus 5 dx. But here, because u squared is 2x plus 5, again, we still need to take the derivative of both sides. So if I differentiate u squared, this is a chain rule job. So differentiating u squared, if I call, for example, y equals u squared using the substitution, dy by dx will be dy by du, differentiate u squared is 2u, times by du by dx, which can leave exactly as it is. So differentiate u squared, I get this, and then differentiate the right-hand side, I'll just get 2. So I can divide by 2 on both sides. That gives me 1. So therefore, dx will just be u du, which we can use. So again, this time dx, wrong colour, I'm going to say dx is u du. And again, we need to anticipate, looking here, that's not going to help at all with cancelling this x. And so, again, what I need to do is to get x in terms of u, or in our case, u squared. So from this, 2x is going to be u squared minus 5. Therefore, x in terms of u is u squared minus 5, all divided by 2. And because u squared is 2x plus 5, this thing here, I'm square rooting u squared. So therefore, I can also say, like a spider diagram now, that u, considering just positive root only, I can say u is going to be root 2x plus 5. So putting all those pieces together, not doing very well with my colour coding today, putting all those pieces together, the original integral will be transformed to the following. So x is u squared minus 5 over 2. Root 2x plus 5, we've seen, can just become u. I'm putting in brackets just to emphasise. Then dx is u du. So we've got our raw ingredients put in. Now it's just a case of neating it up and solving. So of course you can hopefully see here there's a factor of 2, so I can take out that factor of 2. I'll just keep that to one side. So I'm going to have a half u squared minus 5 multiplied by u squared du, because we've got u times u here, just remember, so it's u squared du. We can now expand out and then proceed. So we've got a half u squared times u squared is u to the 4, and then we're going to have minus 5 times u squared, which is just obviously minus 5u squared du. So we can now just integrate this, leaving the half on the outside. So that's going to give us a half u to the 4. The 4 will become 5 and divide by the new power, so it goes to 1/5 u to the 5. Minus 5u squared will integrate to something to do with u cubed. So I'm going to put 5u cubed, but then I need to remember to divide by the new power, so that'll be 5/3 u cubed. Then of course plus c. Before I did this step and then simplified with u and then subbed in. Let's see if we can just skip this step. So 1/2 times 1/5 is going to be 1/10. U to the power 5. Well, u to the power 5, initially u, of course, we put in terms of u squared, not u. And so u is root 2x plus 5, which we can even think of in terms of index form to make it simpler to see. u is 2x plus 5 to the power of 1/2. And so u to the 5 is going to be this, again, to the power 5. So power half times power 5 using indices is going to be is going to be essentially 2x plus 5 to the power 5 over 2. 1/2 times 5, power of a power. Then minus a half times 5/3. Well, half 5/3 is 5/6. So then minus 5/6 u, which is this to the power half, cubed. So 1/2 times 3, that's going to become a new power of 3/2, plus, of course, c. So I personally think that this substitution is easier than part B, but the whole point of this worked example was, I believe, to show that sometimes there's more than one valid substitution. So that's your grounding. Let's now move on to a second one. This time, use the substitution u equals sine x plus 1 to find the integral of cos x sine x multiplied by 1 plus sine x all to the power 3 dx. So let's just set out our working down the side. Okay, so what we're told here is we're going for u being sine x plus 1. Or 1 plus sine x, doesn't really matter. Same thing, different order. So if we just say u is sine x plus 1, we can differentiate u with respect to x. 1 will vanish, sine differentiates to cos. So therefore, rearranging dx becomes du all divided by cosine x. So dx, I can say, is du over cosine x. Then, to be fair, we're pretty much ready to get going, apart from, because you see this cos x on the bottom, that'll help to cancel that one. But that sine x is tricky. That sine x is going to remain. So again, this is where you need to be thinking, well, if the du part doesn't help with the entire cancellation, maybe I need to get the sine x in terms of u, which is exactly what we need to do. I can barely speak today, I don't know what's wrong with me. So u equals sine x plus 1. Just a simple rearrangement of that, we can see that sine x will just be u minus 1 by just subtracting 1 from both sides. So therefore sine x, I can say as u minus 1. And then the cos x here on the bottom will cancel with that cos x. So we're actually ready to go now. So this integral becomes cosine x multiplied by sine x, which in terms of u is u minus 1, multiplied by this. 1 plus sine x, so is u. That's cubed. And then dx tagged on the end, and dx we've shown is du all over cos x. So just to emphasize what's happened, I've replaced sine x with u minus 1. I've switched 1 plus sine x with u, and I've switched dx in terms of du like so. The next thing we can do is spot that cosine x will cancel with this because I'm dividing by cosine x. The next step, just let's rewrite this slightly simpler now. So it's going to be with respect to u. I've got u times u cubed, which is u to the 4, minus 1 times u cubed. I'm just expanding the brackets out. That will give u cubed. Close brackets, and then I'll have du. I can then go forward and just solve, essentially. So if I integrate u to the 4 with respect to u, that'll just give 1/5. Actually, I don't really need brackets. I'm going to change my mind. So that'll give me 1/5 u to the 5 minus u cubed. The cubed will become power 4, and divided by the u power gives me a quarter, or minus a quarter, u to the 4 plus c. and then always remember to pop back in the original variables. We weren't talking about u, that was our substitution. Originally, we were talking about in terms of x. So using the fact that u is sine x plus 1, we just put that back in, and that's our final answer. So u5 is sine x plus 1 to the power 5, minus a quarter u to the power 4, that becomes minus a quarter sine x plus 1 to the power 4, and plus c is just plus c all day long. So that's what we get. Now this is just what I'm calling it. It's not actually known as the special substitution, but I think it's quite special, so I'm going to call it special. It's beautiful, I think. So when we have an expression in the form some constant on the top divided by some constant which can be factorized out, not necessarily the same constant, so I'm calling this one a, but I can factor out some constant and get 1 minus x squared, all rooted on the denominator with respect to x, we can use special trigonometric substitutions. We can either let x be sine theta or x being cos theta, depending on the particular question. So the particular question here, we're going to prove that this integral goes to arc sine x plus c. We're talking in terms of sine x, so that's going to be the clue that let's just check using the substitution x equals sine theta. So if x were equal to sine theta, we can take du by dx. Sorry, I'm so used to talking about in terms of u. We've not even got a u here. What am I talking about? It's x and theta. So if I differentiate x, I mean to say, folks, dx by d theta will be cosine theta. Therefore, dx, this time I need to multiply both sides by d theta. I know technically you can't because we're talking about exact operators here, but thinking of them as fractions, just times d theta by both sides, get cos theta d theta. So dx, I can say, is cos theta d theta. So let's just pop this in. So this integral, we can transform now. What we're going to have, it's going to become integral of 1 over 1 minus x squared. But of course, we said let x be sine theta as our substitution. So this is going to become 1 minus sine theta all squared, which of course is sine squared theta, is what we write. All by dx, but of course dx now we're saying is cos theta d theta. Now, this is the beauty. 1 minus sine squared, of course, is cos squared. So it's 1 over root cos squared theta times cos theta d theta. So what is the square root of cos squared? That's going to be cos. And so what's going to happen here? Cos theta will cancel with that. And so we're just going to have the integral of 1 d theta, which of course is just, if I integrate 1 with respect to something, it's just going to go to theta, plus of course a constant of integration. Then we need to remember what we actually did in the first place, because theta certainly isn't the same as arc sine x. So now we just say, but we said x is sine theta. So therefore, doing sine minus 1, as you say in GCSE, what we say in A-level is arc sine. So theta is going to be sine minus 1x, which in terms of A-level speak is arc sine x. So now, using this, we can just put it back in terms of x. So this here becomes arc sine x and plus c is just, of course, plus c. Just using this idea that again, go back to theta, we need to take arc sine. So theta is arc sine x. So that can also be used with cosine theta. So for example, a similar question might be proving this or something similar gives arc cos x, try the substitution x equals cosine theta. So if you're trying to prove something's arc sine x, sub in x to be sine theta. If it's in this form, if it said arc cos theta, you'd be trying the substitution x equals cosine theta. You might need this in the actual exercises in the Edexcel book. Finally to mention, in the rare cases that a substitution is required but it's neither obvious nor explicitly provided, the general strategy is to substitute for the more difficult expression. So let's have a look at two final examples. Well, 4a and 4b. Before that though, just once again, if a substitution doesn't lead to a helpful cancellation, you might need to rewrite the initial variable in terms of a substituted variable. So, a and b. These ones are definite integrals. So it says here we must use integration by substitution to evaluate these. So even though you could do this by expanding out, not that I'd say that would be wise at all, you must do as a question asks. So a and b, let's try these two. Just section them out so we don't get in the way of each other. So first off, this one, x brackets x plus 1 cubed. So I'm hoping you'll see that the harder bit is the x plus 1. So we're going to say, let u be x plus 1. So I'll just do the writing, sorry, the working, just down the side in a little box here. Then we can obviously put the substitutions in after. So if I just say here that u is x plus 1, du by dx, of course, will just be 1, because 1 disappears when you differentiate it. Differentiate x goes to 1. So therefore, du must be the same as dx, or dx is the same as du. So I've got what dx is in terms of u. It's one and the same thing. What I need to do though here, as you can see, this isn't going to help with getting rid of the x. So I need to rewrite x in terms of what u is. And so x, if I just subtract 1 from both sides, it's fairly obvious, I should hope, that from this here, from our substitution, x will simply be u minus 1. So we're ready to rock. So this is going to be integral from 2 to 0 of x, where x is of course now u minus 1. X plus 1, well, we've called that u. And dx is the same as du. So x becomes that, x plus 1 becomes this, dx becomes du. Going one better, we can obviously expand this into a more workable form. So it's integral from x being from 2 down to 0. U times u cubed is u to the 4. Minus 1 times u cubed, of course, is just minus u cubed. So we can now integrate this. So u to the power 4 would integrate to 1/5 u to the power 5. Minus u cubed would go to 1/4 u to the power 4. In between the limits of x being 2 and 0. Now the book suggests you might want to change the limits, so I can change these in terms of limits for u. I find this can be just another way that students can make a mistake. I sort of flip-flop as I explain things. I might go back and change my mind in future years, but my feeling now at this stage of my teaching is that changing the limits is just an extra potential to make a slip. I find it tends to be easier to just think about what u is in terms of the original variable. So u, just put it back in before we do the integration. before the substitution, I mean to say. So we've got 1/5 u, which is x plus 1 to the power 5 minus 1/4 u, which is x plus 1 to the power 4, with x being from 2 to 0. If your teacher says, don't do that, keep it in terms of u and change these limits, that works too. The book explains it very well. Just check the book, whichever method suits. But I'm using this particular way of doing things. So all that's left to do now is just to actually sub in. So when x is 2, that's going to give us 1/5 times 2 plus 1, 3 to the power 5. So it's 1/5 of 3 to the power 5 minus 1/4, x plus 1 still 3 to the power 4. And I'm not going to have enough space, silly me. Let's make some space here. Then I'm going to have to minus what we get when we input the lower limit of 0. So when x is 0, x plus 1 is just going to be 1. That to the power 5 is just going to be 1 to the power 5, which is 5. So I'm minusing off 1/5, and this becomes minus 1/4. So you can do this in one fell swoop on your calculator if you're confident. Let's just check it. Let's see if it works. So what we're going to have here, just inputting what we need. Put brackets in, 1/5 times 3 to the power 5 minus off 1/4 multiplied by 3 to the power 4, close, and minus brackets 1/5 minus 1/4. Press equals. We get 142 over 5. I did say you can check on the calculator as well, which I'm just going to mention now. If you have integration with limits, a definite integral, if you have time in your exam, always make use of these great calculators to check your answer. So my strong suggestion, almost an order, I can't order you because I'm not a general, try it, see if it works. So different calculators. I think now Casio have made a different brand of ClassWiz. I'm still stuck in my ways. I love this one instead, actually. Again, Casio aren't sponsoring me for this video. They've got better things to be doing. But anyhow, just to show you what I mean, just double check it. So what I was actually doing, I was trying to integrate this thing here. Yep. So if I use my calculator, press the integral button, I'm going from the integral from 2 at the top, lower bound 0, x, so I need to type in x. On this one, it's press alpha and bracket alpha x plus 1, close bracket, that's all cubed. With respect to x, press equals, and it's a nice relief to check actually you've done it correctly. So if you have time on the exam, do check. If this were different, then obviously you've got time hopefully to patch up any errors. So always check and use the power of your calculator at the end to see if you've got it correct if possible. Sometimes you can, sometimes you can't. You can though normally if it's a definite integral. Part B. This one again, we're not told what substitution to use, so using the general rule of subbing for the harder thing. Obviously I'm hoping you can see here root 1 plus sine x looks more horrible than just cosine x on its own. So for B, what I'm going to suggest we do for B is we set u as x plus sine x. Differentiate both sides, so du by dx just goes to cosine x. Therefore, in terms of du, dx is just going to be du all over cosine x. So this dx we can replace with du over cosine x. We say that u is 1 plus sine x, so this will be just root u. And then cos x, well luckily this time, this du, we don't need to do anything. We can leave cosine x as it is, because if you look here, our switch for dx in terms of du, that dividing by cosine x will allow this to cancel, which is great. So weirdly, 4b is actually slightly easier. We don't need to do that extra legwork. So transforming, you're going to go from pi over 2 down to 0 of cos x. This is root u, so I'm going to say u to the 1/2, multiplied by dx, which is du over cosine x. So just to emphasize, that's our u. Dx is du over cosine x. However, now I'm dividing by cosine x here, timesing here, so that neatly cancels. So what I'm going to have now is the integral from pi over 2 down to 0 of u to 1/2 du. Integrate u to the 1/2. That's obviously just going to go to 2/3 u to the 3 over 2. So I've got 2/3 u to the 3 over 2 between pi over 2 and 0. But u, I said, is 1 plus sine x. So it's 2/3 of 1 plus sine x in between the limits of x being pi over 2 and x being 0. Just emphasizing that u is 1 plus sine x. You can use your calculator. In fact, I'd recommend it. But if you do know and are comfortable knowing that pi over 2 in old money is 90 and sine 90 is going to be 1, we can just go ahead and do it. So this is going to become 2/3. Again, don't need the brackets, but I'll just leave them in there. So we're going to have 2/3. That's going to become 1 plus sine x, which just becomes, oops, I forgot the power as well, my bad. That's 3 over 2, so I need that to be 3 over 2 there. I do apologise. So that's going to give 2 to the power 3 over 2. Then minus off 2/3. When x is 0, sine x is 0. So that's going to become 1 to the power 3 over 2, which is just 1. So 2/3 of 1 is just 2/3. So obviously I've got 2/3 as a factor in each term. Once again, I've sort of misjudged the space I have left on the page. So if I just shuffle it along here, what I would say as well is this 2 to the 3 over 2, that's the same as 2 times 2 to the half. So just to be thinking how can I make this a bit nicer, I can say it's the same as 2 root 2. So finally, in a nicer factored form, 2 to the power root 3 over 2, I can say it's 2 root 2, and that becomes minus 1 when it's factorised. So as you've probably seen, these subs are harder, but as long as you follow the rules and the procedure, they are actually doable and nothing to fear. The only thing to fear is not practicing, I think, in A-level. So set to it, try some of these on your own. Turn now to 306 and 307, exercise 11E. Do them all, be a beast, work through every single question, do not stop until you've mastered them. If you're stuck or struggling, which you probably will, if you don't, you're doing great, but to struggle is to learn. Let me know when you get to the stage where you are struggling, come for help, and I'll do my best to try and sort you out with these substitutions. Thank you for listening once again, and I hope to see you all soon. Take care until then.